Hey everybody, so we're back for our final installment before the end of the acid-base unit. So we're on episode 12, and episode 13 will be the first one that goes into the hydrolysis unit, which is related to acid-base, but so I guess formally if you were doing your acid-base unit, you might have like a unit test or something like that at the end of this. I know my classes would be, that's kind of where we would be at this point. Today's class is about kind of the last thing. It's Bronsted-Lowry reactions. Not that you haven't been doing them before, but Bronsted-Lowry reactions between acids and bases where water's not one of the two components. Water will be there, and you'll see that there's a complication by adding in other chemicals, and what acts as the acid, what acts as the base. Are there choices? Do other reactions go on at the same time? How does a predominant Bronsted-Lowry equation or reaction come out of all of this? How do you label that? How do you know it? So what we'll do is we'll go through some of those things. I've only put two topics up here on the list. Number one, defining, identifying, and then Bronsted-Lowry reactions, and then labeling the acid, the base, and the conjugate acid, conjugate base. And then also, how can you determine the KEQ of that Bronsted-Lowry reaction? How do you determine whether products or reactants are favored based on that, which is actually a concept that you learned way back when you were first doing equilibria. And then we'll tie it into what you already know about acids and bases, and you'll see that all of those previous reactions that we've done before, they kind of follow the rules that you've been using for calculating Ks and Kbs and whether products or reactants are favored in weak and strong acids and bases. So it all kind of fits together by the end of this day. And then, like I said, next class is going to be the introduction into hydrolysis, and we kind of move on from there. Okay, so defining and then identifying a Bronsted-Lowry chemical reaction. So the idea of a Bronsted-Lowry reaction is the plain and simple fact that one proton gets moved, transferred from one chemical to another. So I guess the first thing that you're going to notice about a Bronsted-Lowry reaction is you'll have two reactants. You have to have two reactants. You have to have one molecule bumping into another molecule. And when that occurs, an H will be transferred. And you will see that in what you have as the products. So if you kind of follow one chemical reactant to its, what is quite obviously its partner on the other side, on the product side, you'll see that the difference between the two of them is one proton. It will either pick up a proton or it will lose a proton. And depending on what you see in the actual equation, you can kind of tell what chemical was acting as what. Okay, so Bronsted-Lowry reactions are those that have the transfer of a single proton. How do you identify them? You identify them by looking at your reactants and your products and seeing if in fact one chemical lost a proton during that process and one picked up a proton, or an H, as it were. Okay, and then labeling. So I've got an example up here on the board. So this reaction that's up here, one, water's not involved. Now I didn't, because I kind of had limited space up there, so I didn't write little AQs, but these are ions, or 3 of the 4 of them are ions. The other one is a covalent compound that would form a molecular solution. So I'm making the assumption here that all of these things are dissolved in water. So you have to kind of go along with me. I just didn't write the little AQs for all of them. So how do I know this is a Bronsted-Lowry chemical reaction? So what I do, and the simplest thing, I think the simplest thing for my eye, is to pick one of the two reactants. It doesn't even matter which one. So I'm going to start with the one that's on the left. Okay, so I'm going to start with this one right here. And then what I'm going to do is I'm going to look at the product side, and I am going to decide which of the products is related to it or looks related to it. And I think it's quite obvious that this one is related to it. and now that you're kind of at the end of the acid-base unit, maybe you've been doing some homework, you've been doing some of the practices and maybe some of the quizzes, pardon me, your teachers have been giving you, that you start to recognize these things very easily. Okay, so you've got bicarbonate or hydrogen carbonate over here on the left-hand side, on the reactant side, and you've got carbonic acid over there on the right-hand side. So you've probably recognized those things. So you've got an HCO3 minus, and over on the right-hand side, you've got an H2CO3. Those two are quite obviously partners. And what has happened is they are 1H apart, because one of them is, they both have CO3. One has 1H and one has 2 H's. So obviously this guy over here is 1H less. Sorry. This guy over here is 1H less than this guy. And so to go from here to that chemical, it needed to pick up an H. So as long as the other two chemicals in the reaction lost that H, then this is going to be a Bronsted-Lowry reaction. So this guy is partnered with this guy. So you can kind of see that these two are paired, and these two are paired. And so these two, this guy had 2 H's, PO4, so that's called dihydrogen phosphate. This guy has 1 H, so that's monohydrogen phosphate. This guy lost an H in the process of going from H2PO4 minus being a reactant over to HPO4 minus 2 being a product. So the chemical reaction here is a Bronsted-Lowry reaction because a proton went from this chemical, gave up a hydrogen, this chemical picked up a hydrogen. So the transfer was between those two things. And the result of that transfer of an H from one to the other were those two chemicals over there on the product side. So this is in fact a Bronsted-Lowry equation. And you'll see that with any Bronsted-Lowry reaction that you have, you'll be able to identify kind of the pairings of a reactant with a product and the fact that they're 1H different. And you'll see that as one partnership loses an H to become the product, the other partnership will gain that H. Okay, and it really is that simple. You can see it in any one of the reactions. Labeling them though, so then you have to look kind of closely at what these things are actually doing. So when I'm labeling, I'm going to go with blue. So when I'm labeling, I'm looking at my partnerships here. Okay, and so what I need to do is I need to focus on each side of the equation. So each side of the equation will have an acid and each side of the equation will have a base. So as I'm going from left to right, the things that are on the left-hand side, as they go to the right, the things on the left-hand side, one chemical will act as the acid, one will act as the base. An H will get transferred from the acid over to the base. When I go to the other side of the equation and I look at the right-hand side and I go back the other way, going back the other way, an exchange of an H will happen as well as you go from right to left in the reverse direction. That H, again, will go from the acid that's over on this side over to the base, and they will go back to the other side of the equation. And so each side has its own acid-base combo. So over here on this side, I'm going to erase these things just for a sec. Over here on this side, which thing was giving up the H? Well, we decided that the H2PO4 minus gave up the H as it became that. So this gave up the H to that. Therefore, the H2PO4 in the forward direction was acting as the acid. This was therefore acting as the base. Okay, in the forward direction, and that's kind of important. Like actually using the words forward and reverse here is pretty important. But if we're going in the reverse direction, then okay, so now kind of change your brain to see things from right to left. When you're looking right to left, which of these two chemicals over here turned around and gave an H? Okay, so which thing is acting as the acid in the reverse direction? Well, this guy went from H2CO3 as it went right to left back to HCO3. So this guy is acting as the acid. However, this guy right here and this guy right here are partners. So they're partners, and the word that we use in Bronsted-Lowry kind of terminology, nomenclature, is conjugate, and that means the partnership. So this thing is not just the acid in the reverse direction. This happens to be the conjugate acid. So it's the conjugate acid to HCO3 minus. It's the acid going in the reverse direction. This guy will therefore be the conjugate base. So because H2PO4 was acting as an acid in the forward direction, this guy is acting as the conjugate base, the base, going in the reverse direction. Okay, so you got to kind of see things as two opposing little reactions. There's an acid and a base going in the forward direction, and then there's an acid and a base, which we refer to as the conjugates, going in the reverse direction. Okay, and that's when someone asks you to label that, they might ask you, what is the acid in the reverse direction, or what is the conjugate acid? And so it's just a matter of labeling it, okay? In a minute, I'm going to give you an example of, well, how do you figure out what the missing part is? And we'll show you that in just a sec. So I've labeled it, okay? You will see that if you go with what you've already, like some of the reactions we've already done. So if I put in, for example, if I put in HSO4 minus plus H2O in equilibrium with H3O plus SO4 minus 2. Is that a Bronsted-Lowry equation? The HSO4, there's its partner over there. It lost an H in the process of becoming its partner. This is the acid in the forward direction. This is the conjugate base in the reverse direction. The water has the ability to pick up an H, so it became that. So this is the base in the forward direction. H3O plus hydronium is the conjugate acid. It is the acid in the reverse direction. So again, this is just a typical equation or Bronsted-Lowry reaction that we were using before. This is the one you would use if you were calculating the hydronium concentration of an HSO4 minus solution to get the pH of it. Like, this is what you would have. So this does fit into something similar to this. Now, you might ask the question, well, when would this ever occur? So that would occur if you happen to mix two solutions of HCO3 minus and H2PO4 minus and mix them together. So you would have HCO3 minus, you'd have H2PO4 minus, and you'd have water. All three of those things in the solution. And so what would happen is you would get the reaction that happens the most frequently would be the predominant reaction. And so it's almost as if you think about this, something like HCO3 minus has a choice. When you dump it into water, does it bump into H2PO4 minuses more frequently, and does the H2PO4 act as a better acid than if HCO3 minus bumped into water? And so those collisions are happening all over the place. HCO3 minus will react more predominantly with the thing in the solution that acts as the better acid. Well, H2PO4 minus is a better acid than water. And if you look at your Ka table, okay, so I'm going to pull out the Ka table here, and you look for water as an acid. Water as an acid is down here. It is, like, it's terrible. It's the one above the grays that don't act as acids. Like the Ka of water is actually the Kw, so it's 1 times 10 to the negative 14. It is as an acid goes, it's terrible. So it's really, really bad. All of these acids up above it are going to be better than water. So you take HCO3 minus, put it into a solution of H2PO4 minus, and it's got a choice. Which chemical will you do a Bronsted-Lowry reaction with? It'll pick the one that acts as the better acid, which, according to the table, would be H2PO4 minus. Okay, and so you'll tend to get that all the time. In this reaction here, we obviously took HSO4 minus, put it into water, and there was no other options. HSO4 minus, if it was going to act as an acid, only had water molecules to react with. We didn't give it that choice. If we put something in that was a possible base, and it was a better base than water, and again, water as a base is right up here. So it's the first one of the white section there. So as bases go, it sucks. So water is terrible as an acid. It's terrible as a base. So you give an acid anything to react with other than water, and chances are it's going to react with it. So in this case, HSO4 minus didn't have a choice. It had water and only water. If I put something else in there, it would have chosen something else. Okay. Now, obviously, chemicals do not think. They don't choose. They don't go, well, I'm going to ignore you over there and I'm going to pick this one over here. It's more a matter of probabilities and statistics. Really, it comes down to math, where if let's go back to this one. If HCO3 minuses are bumping into things in solution all over the place, they happen to react easier, like if the actual reaction occurs easier with H2PO4 minuses. So when those collisions occur, they happen at a higher frequency than if HCO3 minus bumped into water. Okay, and so the predominant reaction is not what HCO3 wants or is thinking about or anything like that. It comes down to the probability of whether or not the collisions are going to lead to a successful reaction or not. And so that probability is higher when you had H2PO4 as an option rather than just water. Okay, so that's a little bit of a kind of a complex idea that these things come down, predominant reactions really come down to the mathematics of it, the statistics, the probability of it. Okay. Now, I said I was going to show you one example of fill in like the missing piece. So what if I gave you a reaction, or somebody asked you to do the following? So they went something like, let's go with HC6H5O7 minus 2 plus HC2O4 minus in equilibrium with blank plus, let's go with C2O4 minus 2. And then they asked you, fill in the missing piece. What is the missing piece? Okay, so what you would do is you'd have to say to yourself, okay, number one, is this a Bronsted-Lowry reaction? Is it a reasonable thing to assume this is a Bronsted-Lowry reaction? And if so, what thing in the forward direction is acting as the acid? What thing is acting as the base? Of course, you could be, the blank could have been anywhere. As long as you know the other three parts, you'll be able to figure this out. And so the only thing you can base this on is the comparison of the two partners. Okay, so C2O4 minus 2 and HC2O4 minus 1, there's only a very minor difference, and it's a hydrogen. So over here, it has the hydrogen. Over here, the hydrogen's taken off, which means that this was acting as the acid in the forward direction. Right? Which means this thing, whatever this thing is, has to, if a Bronsted-Lowry reaction was occurring, this thing had to have been acting as the base. Now, both of these things that I've got over here, both of those things are amphiprotic. So they both have H's, they both have negatives. So the H could have been exchanged the other direction. But don't worry about the math. You're being given that this is one of the products. Okay, so I'm not going to worry about, once I kind of introduce to you, comparing KAs, which side's dominant and all that kind of things. What I want you to do is I want you to just look at what the product is, and the other one must follow suit. If this reaction was going to occur, and an H came off to form the C2O4, that H must have gone on to this thing. So it went from H, a single H, and that's monohydrogen citrate that's over there, and H must have gone on it, which means the missing piece must have been H2, C6, H5O7, and what charge would it be now? Well, it was -2. We've put a +1 on it, so it has gone up on the number line from -2 to -1. Okay, and that would be the missing product that was there. Okay, and if you were asked to label it, base acid in the reverse direction, this would have been the conjugate acid, conjugate base, just like I did up above. Okay, so the last thing is, can you determine a KQ for these things? Now, KQ for these things, you'll notice that there's no hydronium or hydroxide that's in there, which means we're not using the KQ to do any kind of math calculations in terms of what's the pH of the solution. That's not what it's for. The KQ for these reactions is solely to determine which side is favored at equilibrium. Okay, so if we allow the top one, to come to equilibrium, where the rate forward and the rate reverse equal each other. And once the rate forward and the rate reverse equal each other, that means as soon as these turn into those, an equal number go back the other way. And so the rates are balancing each other, and there's no net change between the forward and the reverse. It does not mean they have to be at the same concentrations. That's not what equilibrium is defined as. Equilibrium is defined as the rate forward equals the rate reverse, not the concentrations of the reactants equal concentrations of the product. That's not the definition. And if you thought that was the definition, maybe you need to go back and kind of recheck the definition of equilibrium at the very beginning. So rate forward equals rate reverse, and more likely than not, the concentrations of the reactants in the products are not going to be equal. That's going to be 99.99999% of the time. The only time they do equal each other is if you've got a KQ equal to 1, and then it's equal on either side, because that's how you get the ratio. So the KQ is going to determine which side is being favored. Now, I want you to think of these Bronsted-Lowry reactions as a battle. Okay, so if someone ever asks you which side is favored in this Bronsted-Lowry reaction, think of it as a battle between two acids. Okay, so it's the forward acid versus the reverse acid. So once you've labeled things, you've got an acid here in that direction. So this guy's trying to unload an H onto HCO3 and push the reaction in that direction. In the reverse direction, you've got that acid pushing that way. Okay, so this is trying to push back the other way. Really what you have is you have a battle between H2PO4 going this way and H2CO3 going that way, and they're fighting each other, right? They're trying to push to the other side. If you're thinking of this as a battle between these two acids, the stronger of those two acids is going to win the battle. And if this guy over here is stronger than this guy pushing back, then it's going to kind of push this away. And you're going to end up with more things over here on the product side. And that's what we refer to as products being favored. The stronger the acid, it pushes to the opposite side. And that side then ends up being favored. So don't think of favored as where the stronger thing is. The stronger thing pushes towards the favored side. By favored, that means higher concentration at equilibrium. Okay, so like I said, equilibrium is when rate forward equals rate reversed, but concentrations aren't necessarily going to be the same. The favored side has the higher concentration at equilibrium. So once it reaches equilibrium, which side has the higher concentration? That's the side that's favored. So how do you determine this which side is favored? You can come up with a numerical answer to it. Okay, so this is an equilibrium, which means it has a KEQ. And that KEQ, I'm going to give myself a little bit more room here, sorry. And that KEQ can be calculated by comparing the forward acid to the reverse acid. And you can compare it because you have a table of Ka values. So what you want to do is you want to take a look at the relative strengths. And you can do that mathematically by taking the Ka of the forward acid. I'll just put forward. I don't need to write the word acid. The Ka of the forward over the Ka of the reverse. So you've got this acid going that way, you've got this acid going that way. And you can look up the Kas of those two acids on the Ka table. You can actually put them in and you can do the actual math to get a value of KQ. So according to my table, right, glasses, here we are. So the forward acid was H2PO4. So H2PO4, where is that dihydrogen phosphate guy? 6.2 times 10 to the negative 8. So 6.2 times 10 to the negative 8 over H2CO3, 4.3 times 10 to the negative 7. Okay, so forward acid, 10 to the negative 8, reverse reaction, 10 to the negative 7. Probably in your head figure out what that is, but I'm going to actually do the math. So that comes out to 6.2 exponent 8, negative 8, sorry, divided by 4.3 exponent negative 7, and I get 0.14 as my answer. Okay? So this thing has a KQ of 0.14. Now, that doesn't tell you anything in terms of pH or pOH because hydronium and hydroxide are not part of this equation. So you can't use it to solve anything in terms of pH. Okay? That's whole nother chapter. So that's back when we were doing all the weak acid, weak base stuff. So this value, what does it tell you? So this right here, the word evaluate. So this allows you to evaluate this equilibrium. And it tells you something about products over reactants. Because the KQ is equal to the ratio of products over reactants. That's what it is. Any fraction, so less than 1 but greater than 0, any fraction means that the bottom of the ratio is greater than the top of the ratio. Right? If it was 1, the top and the bottom, the numerator and denominator, would be the same value. If it was greater than 1, the top of the numerator would be bigger than the denominator, and so products would be bigger than the reactants. This ratio is less than 1, greater than 0, because you can't have negative. So the reactants must be a larger concentration at equilibrium than the products are. So since KEQ is less than 1, reactants are favored. And if you recall from the equilibrium unit, anytime you had a KEQ less than 1, reactants were favored. How much less than 1? Like, are we talking like this one, 0.14? Or are we talking 0.00000014? How small it is tells you kind of the discrepancy between the products and the reactants. And so if you had 1 times 10 to the negative 12, then that's telling you that the reactants really outweigh the products, not just by a little bit. So in this case, 0.14, reactants still outweigh the products, but not by quite that much. If we had a KEQ, if we did this and it came out to 5, then that's telling you that the products outweigh the reactants by a ratio of 5 to 1 kind of thing. And if it was 1 times 10 to the 28th, then it's telling you that the products way outweigh the reactants at equilibrium. Okay, so it gives you some sense that if you mix these two things, right, if I put them together and they did this reaction as it is written, if they did this reaction as written, then the reactants would be favored at equilibrium. Okay, so they would react, but you'd have more of these at equilibrium than you have of those things at equilibrium. Then you can use that value, that Ka of the forward acid divided by Ka of the reverse acid, you can use that value to evaluate the equilibrium, whether or not your products or reactants are favored at equilibrium. And that's kind of the last thing that we're going to go through in the acid-base unit. So you can actually use that information to answer a whole bunch of questions if you kind of get that idea. Okay, if you get that concept of what the KEQ is telling you about that mixture. Okay, so that's kind of how I would go through the acid-base unit. So we'll start the hydrolysis in the next episode. So feel free to subscribe, and when that video is posted, you'll get the notification, and then you can start your hydrolysis unit. Okay, so hopefully that was good, and we'll see you next time for hydrolysis.